Which one of the following is the correct term for the gravitational force the Earth exerts on any object on or near its surface? This very same question was there in the June examination, and the answer is A, weight. Weight is the gravitational force that the Earth exerts on any object on or near its surface. It's just one of those definitions that we overlook, but look at 1.1. You needed to know what weight is. Let's go ahead and do 1.2. The driver of a truck places a suitcase on the level dashboard in front of him. He observes that the suitcase is sliding towards the windscreen. At the instance, the truck is probably moving. Okay, so we're supposed to choose between a few options there. We have our dashboard, which is level, and there's a suitcase on top of the dashboard. The suitcase is sliding towards the windscreen. Why do we keep our seat belts on in the car? So that when we experience inertia, there is something holding us back. The suitcase is experiencing inertia. It wants to keep moving at the very same speed that it was moving in. That tells us that the car is slowing down. That is why the suitcase is moving forward. If the suitcase was moving backwards, then the car will be starting to speed up. So the answer to 1.2, we have forward and slowing down. The car is moving forward, but it is slowing down. Our suitcase is experiencing inertia. So the answer to 1.2 is C. 1.3. A stone is thrown vertically upwards. Which one of the following combinations correctly represents the stone's acceleration and velocity 1 second before reaching maximum height? Assume that air resistance is ignored. Usually, we are interested at maximum height, but now we are interested at 1 second before the maximum height. Before I even look at the options, I know that the acceleration is 9.8 meters per second squared downwards. That is not up for negotiation. So option B and option D is the only two options I'm looking at. Now let's think about the velocity. Well, our object is thrown vertically upwards. So before it reaches maximum height, it must still be moving upwards. At B, we have 9.8 meters per second upwards, and at D, we have 9.8 meters per second downwards. We know obviously that our answer is gonna be B. Our object is still moving upwards. It hasn't reached its maximum height. But you can also get to B being the answer using another thought process than the one I'm using. Yeah, I have it in my head, but I'm just going to keep it to myself. Let's move to 1.4. We have 1.4. A car approaches a road with a lower speed limit, and the driver slows down the car. The two vectors, momentum initial and momentum final below, represent its initial and final momentum respectively. Initial and final. Which one of the following vector diagram correctly represents the change in momentum of the car? A lot of people will probably think that P initial and P final are pointing in the same direction. So I can just add them and my answer will be A. But that is not the case. We're looking for the vector that represent the change in momentum. P final minus P initial. So let's go ahead and have that. For P final, the vector looks something like this. This is P final, and we're supposed to subtract P initial to find the change in momentum. So if we do that using the tail to head method, we're going to have something that looks like this. This is our P initial. This is our P final. And here is where we have our change in momentum. Clearly, the answer is D. Let's move to 1.5. So what do we have in 1.5? An object is dropped from a height h above the ground. Dropped, what does that tell us? Vi is equals to 0. Let's carry on. Which one of the following graph best represents the relationship between its kinetic energy and its height above ground level. Let's think about that. At our maximum height, v is equals to 0 meters per second, because our object is just getting dropped at maximum height. And when the height is equals to 0, our object is striking the ground. So we have v max. Without even looking at the options, we can deduce this just from vertical projectile motion. So let's try find a graph that supports what we are saying, which we know to be true. Here, as the height is increasing, the kinetic energy is increasing. This cannot be true. When the height is increasing, we need our kinetic energy to be decreasing because v is equals to 0 at the maximum height. If we look at option A, when the height is at its maximum, we have a kinetic energy of 0. So v is equals to 0. Let's look at when the height is equals to 0. Do we have maximum kinetic energy? When the height is 0, you can clearly see that we have maximum kinetic energy. I don't think we have to look any further. It seems like our answer here is A. Let's go ahead and do 1.6. 1.6, how does the wavelength and frequency of a wave source change when it moves towards the observer? That's quite an easy one. When an object is moving, a sound source is moving towards an observer, the wavelength is going to decrease and the frequency is going to increase. So that is the option we're looking for. Wavelength decrease, frequency increase. So option B, the answer to 1.6. Our wavelength is going to decrease and our frequency is going to increase. 1.7. 1.7. A positive point charge Q1 and a negative point charge Q2 of equal magnitudes are held at fixed positions, as shown in the diagram below. So Q1 is positive and Q2 is negative. I need to put that there so that I don't forget. S is exactly halfway between Q1 and Q2. I don't see any S on the diagram, but maybe they are referring to Y. Let's see, which one of the following combinations gives the correct direction of the net electric field due to the presence of charges Q1, Q2 at positions X, Y, and Z respectively. So when we have a point charge, we can always assume that it is positive. So let's put that there and do some analysis. First, let's look at X. There's a repulsion between X and Q1. So the electric field is pointing to the left. Between Q2 and X, there is attraction. But look at how far Q2 is. The electric field is inversely proportional to the distance between the charge and the point of interest. So Q1 is going to win this battle. At point X, the net electric field is going to be pointing to the left. So we are only looking at option C and option D. Let's go to Y. How is Q1 and Y interacting? Q1 is going to be pushing to the right. They're all positive. So there's a repulsion. And then Q2 and Y, they have opposite charges. There's a force of attraction. So Q2 is also pushing to the right. So at point Y, the net electric field is to the right. No questions asked there. So which option? C and D, they are still all correct. Now we have to move to Z, our position Z. Let's see what happens at Z. Z is positive, Q2 is negative. There is an attraction there. So the electric field is to the left. Now let's look at Q1 and Z. Well, Q1 is too far. So we can just pay attention to the effect of Q2. That is only because they have equal magnitudes. If they had different magnitudes, then our question will be a bit more difficult and we would have to actually consider the distances and the magnitudes in detail. So Z is moving to the left. That is option D. So the answer to 1.7 is D. Let's go to 1.8 and hear stories. So in 1.8, in the given circuit diagram below, the three light bulbs L1, L2, and L3 are identical. X, Y, and Z are readings on the ammeters in the circuit. Which one of the following mathematical equations is correct? Let's do some analysis. Well, what I'm realizing very quick is that at X, we have total current. So this is IT. Our three bulbs are identical. So the current is divided proportionally. The reading on Y is equals to the reading on Z. We don't have a reading on L1, but I don't think that will hinder us to reach a conclusion. Let's look at what makes sense. A says that the reading on Y is equals to X minus Z. Well, that is not true. The reading on Y can be equals to X minus 2Z, not X minus Z. And B, the reading on X, the total current, is equals to 3 multiplied by Y. Here on this path we have Y, here on this path we have Y, and here on this path we have Y. Z and Y are equals to each other. So this is true. Option B is true. So the answer to 1.8 is B. That is true. 1.9, the solid line in the graph below represents the output of an AC generator. The dotted line represents the output of the same generator after a change has been made to the generator. Okay, let's go ahead and do some analysis. Before the change, we have we have two rotations, and after the change, we only have one rotation per unit time for the same amount of time. So what has changed? Our speed of rotation has now been halved. Which option is that? C. So the answer to 1.9 is C. And 1.10, the diagram below indicates an energy level diagram that corresponds with the 4 energy levels in an atom. Which one of the 4 energy transition has the shortest wavelength? Shortest wavelength or highest frequency. The higher the frequency, the higher the energy. S. Option D. A block of mass 2 kg is sliding down a plane inclined at an angle of 30 degrees to the horizontal, as shown in the diagram below. And then there's a coefficient of kinetic friction between the block and the plane, which is 0.2. Then the first question, 2.1.1, we're supposed to define the term kinetic frictional force. So kinetic frictional force is the force that opposes the motion of a moving object relative to a surface. Let's go ahead and look at 2.1.2. Draw a labeled free body diagram for the block while it is in motion. So the marker location is 3. And like I've said previously, if the marker location for a free body diagram is 3, then you should know that your free body diagram will have 3 forces. If the marker location is 3 and you have 2 forces on your free body diagram, you're doing something wrong. And another point I always make is that when you're drawing the free body diagram, before you start thinking about a lot of things, put weight first. Everything is going to come after you put weight. Right, and then now we can go ahead and look at our object. Is our object resting on a surface? Yes, it is. So we have normal force right here. What else do we have? We have the coefficient of kinetic friction, so we have friction. The object is going down the incline, so our friction must be up the incline. So we have frictional force up the incline. Obviously, with our weight, we know that we have the perpendicular component, FG perpendicular, and the parallel component, FG parallel. You don't have to include FG parallel and FG perpendicular, but most likely you will have to use it when you calculate. Let's do 2.1.3. Calculate the acceleration of the block. Right, before we start analyzing our problem, F net is equals to MA. These are just standard things. Now we can go ahead and analyze our problem. We have FG parallel and we have the frictional force. Those are the 2 forces we are interested in. Why am I saying so? Our object is moving parallel the incline. So we are only interested in the forces that are moving parallel the incline. Right, so how do we then set up our equation? So what you want to say here is that the force pulling the object minus all the forces that are opposing. As you can see, the object is going down the incline. This is because of FG parallel. And then the force that is opposing is the frictional force. So we're going to say FG parallel minus frictional force is equals to MA. Now we just need to find FG parallel. Let's do that separately. So FG parallel is equals to mg sine of theta, where m is the mass, 2 kgs, multiplied by 9,8 sine of 30 degrees. So what is FG equals to? This is 2 multiplied by 4.9. And then now we can calculate frictional force. Frictional force is equals to the coefficient multiplied by the normal force. The coefficient is 0.2. And then our normal force, if you look at our free body diagram, the normal force is being balanced out by FG perpendicular. So the normal force is equals to FG perpendicular in this instance, where FG perpendicular is mg cos of theta. So we have 2 multiplied by 9,8 multiplied by cos of 30 degrees. So our frictional force is equals to 2 multiplied by 1.6974. So now we can substitute back into our equation. FG parallel, that is 2 multiplied by 4.9 minus the frictional force, that is 2 multiplied by 1.6974. This is equals to MA. The mass of our object is 2 kgs. The acceleration is what we are interested in. It will be easy to see what we need to do here. We are dividing by 2 on both sides. So let's just go ahead and do that. And we get in an acceleration that is equals to 3.2 meters per second squared down the incline. This right here is 4.9 and not 14.9. But anyway, stories, that is 2.1.3. Let's do 2.2. In two adjacent buildings of the same size, the two walls nearest one another are 7 meters apart, and the walls furthest from one another are 35 meters apart, as the diagram below illustrates. Right, we can see them. And then the question is saying, use an appropriate calculation to show that the gravitational force that the two inner walls exert on each other is 25 times bigger than that of the two outer walls on each other. And then they're saying we need to show that Fg of the inner walls is equals to 25 times of the outer walls. What is Fg? Let's start there. Fg is equals to G m1 m2 divided by r squared. So everything else is constant except from the distance between the two walls. So that is the only variable we are changing. Let's start with the inner walls. So for the inner walls, we're going to have Fg of the inner walls being, let's just say Fg inner, being equals to G m1 m2 divided by r squared. The inner walls are 7 meters apart. So we're going to have 7 squared. We know what 7 squared is equals to. So we're going to have G m1 m2 divided by 49. These are the inner walls. Now we can go ahead and set up the same equation, but now for the outer walls. The outer walls are 35 meters apart from each other. So we're going to have Fg of the outer walls being equals to G m1 m2 divided by 35 squared. So G m1 m2 divided by, what is 35 squared? That is 1225. So here we have Fg for the inner walls, and here we have Fg for the outer walls. Now we need to show that FG for the inner walls is equals to 25 multiplied by 25 multiplied by FG of the outer walls. Let's go ahead and see if this is true. So FG of the inner walls, we have G M1 M2 divided by 49. This is apparently supposed to be equals to 25 multiplied by G M1 M2 divided by 125. G M1 M2 divided by 49 is indeed equals to G M1 M2 divided by 49. To cut the long story short, our ball A has an initial velocity of 2 meters per second downwards, and our ball B has an unknown initial velocity. So ball A and B, they strike the ground at the same time, even though ball B is projected 1 second later. That is the scenario we have. And 3.1 is just the definition. What is meant by a projectile? An object which has been given an initial velocity and then moves under the influence of gravitational force only. That is what we call a projectile. Let's look at 3.2 and 3.2.1. Calculate by using the equations of motion the time taken by stone A to hit the water. So let's go ahead and look at the information we have. The information we have is what's gonna guide us to the formula that we need to use. So I know that VI I always take up as positive, by the way, unless stated otherwise by the question. So VI is 2 meters per second. If I'm taking up as positive, this will be downwards, and I'm going to substitute it with a negative sign. And the acceleration is negative minus 9.8 meters per second squared. Delta Y is negative. I have minus 50. What am I looking for? I'm looking for delta T. When I have these variables, I can use delta Y is equals to VI delta T plus a half A delta T squared. But I don't want to use that formula because my initial velocity is not 0. I'm going to have to solve a quadratic equation, and that is the last thing I want to do. So instead, I'm going to say that VF squared is equals to VI squared plus 2A delta Y. If I find VF, I'm going to be able to use VF is equals to VI plus A delta T and find the time. So VF squared is equals to VI squared minus 2 squared plus 2 multiplied by the acceleration minus 9.8 multiplied by delta Y minus 50. Now I just need to take square root on both sides. I'm going to get VF being equals to 31.3688 meters per second. But I know that it is downwards because the ball is striking the ground while it is going downwards. When I use it next, I'm going to put a negative sign. You need to be aware of that, right? So now that I have VF, I'm going to say that VF is equals to VI plus A delta T. So delta T is equals to VF minus VI divided by the acceleration. VF is minus 31.3688 minus VI. VI is minus 2 meters per second, right? And then we divide it by the acceleration, which is minus 9.8. And then our delta T is 2.99. Well, it is just 3 seconds because we're supposed to round it off to 2 decimal places if it is our final answer. So we have 3 seconds. That is delta T. The question that follows, 3.82.82, we're supposed to calculate the time taken by stone B to hit the water. This is for 1 mark. So just to remind you, stone A and stone B strikes the ground at the same time, but stone B is projected 1 second later. So the time for stone B is equals to the time for stone A minus 1. So this is just 3 minus 1, which is 2 seconds. And just like that, we have the time for stone B. 3.2.3, the initial velocity of stone B. So let's look at the information that we have with regards to stone B, and then an approach is gonna present itself. That's how it works. So we have delta T, which is equals to 2 seconds. We have VI, which is what you're interested in. We have delta Y, which is minus 50, because up is always positive, common sense. And then our acceleration is minus 9.8. What else am I missing? I have delta T, I have VI, I have delta Y, I have the acceleration. What am I looking for? I'm looking for VI. Right, I can use delta Y is equals to VI delta T plus a half A delta T squared. I'm looking for VI, so I'm not going to have to solve a quadratic equation. Yeah, I always run away from solving a quadratic equation. I don't like complicating my life unnecessarily. So delta Y, that is minus 50, and VI, it's what I'm interested in. Delta T is 2 plus a half, acceleration minus 9.8, delta T 2 squared. So how do I set up my equations now? VI multiplied by 2 will be equals to minus 50 minus a half minus 9.8. The time is 2 squared. If I divide both sides by 2, I'm getting VI being equals to 15.2 meters per second downwards. The question says the velocity, so we're supposed to include the direction, just like I did there. Let's carry on. The last question, 3.3, sketch on the same set of axes, position versus time graphs for the motions of the two stones from the instant that they are thrown until they hit the water in the pool. Use the water surface as the zero reference. Clearly show the values on the following on the graphs: time at which the stones hit the water, time at which stone B is thrown, initial height of the stones above the water surface. Right, let's go ahead and see how that is gonna look like. We have our y-axis and we have our x-axis. In our x-axis, we have the time in seconds. So let's just go ahead and put that there. And in our y-axis, we have the change in y in meters. We're starting at 50 meters and we're going down to 0 meters. What is our time? They strike the ground at 3 seconds, right? But stone B is projected 1 second after stone A was projected. So the position time graph for stone A would look something like this. This is stone A. And then on the other hand, stone B will look something like this. There we go. So this is stone A and this is stone B. A bullet is fired horizontally into a 3 kg wooden block resting on a horizontal surface. The bullet remains embedded in the block, which is observed to slide 0.25 meters along the surface before stopping. Refer to the diagram below. We have our diagram, which is not new. We have seen a bullet block system before. The coefficient of kinetic friction between the block and the surface is 0.2. Neglect the effects of air resistance. 4.1. Is frictional force an external force or an internal force? I don't think there's any need to explain that. Frictional force is an external force of a system. External force. Let's look at 4.2. Say the principle of conservation of linear momentum in words. The total linear momentum of an isolated system remains constant. What about 4.3 and 4.3.1? In 4.3.1, we're supposed to calculate the velocity of the block after the bullet has been embedded in it. There's a frictional force between the block. There's a frictional force between the block and the surface. So we cannot use the conservation of linear momentum. I'm not so sure what we're going to use, but I know that when I write the variables down, the approach is gonna reveal itself. So let's go ahead and jot down the information we have and see which route we can take. So I have the coefficient of frictional force. I have the normal force as I have the mass of the bullet and the block. What other information do I have? I have delta x, which is equals to 0.25, and I have VF, which is equals to 0. I have VI. Well, I don't have VI. VI is what I'm looking for. So with these variables, we can try VF squared is equals to VI squared plus 2A delta Y. But you should realize fairly quickly that even though we have VF and VI is what we're interested in, we don't have the acceleration. We have delta Y. So the only thing that we need here is the acceleration. If we have the acceleration, then we can use VF squared is equals to VI squared plus 2A delta Y. But how can we find the acceleration? We can use F net. So we're going to say that F net is equals to MA. There's only one force that is acting on our object, frictional force. So the frictional force is equals to MA in this instance. The coefficient of kinetic friction is 0.2, and we're supposed to multiply that by the normal force. The normal force is the mass multiplied by 9,8. What is the mass? The bullet is embedded in the block. So we're going to have 3 plus 0.005 multiplied by 9.8. This is equals to the mass, again, 3 plus 0.005 multiplied by the acceleration. It is pretty obvious what we need to do now. We are dividing both sides by 3 plus 0.005. They cancel out on the right hand side, and now we are dividing by 3 plus 0.005 on the left hand side. Our acceleration is equals to 1.96 meters per second squared. But we need to make sense of our situation. The bullet block system is moving to the east, and frictional force, it is always opposing. This is 1.96 meters per second squared to the west. We need to put that into account. Now that we have the acceleration, we can find VI. So we're going to say VF squared. So we have 0 squared being equals to VI squared plus 2A. Our acceleration is minus 1.96 multiplied by delta Y, which is 0.25. If we take direction to the east as positive. If we solve this, we're going to get VI squared being equals to 2 multiplied by 1.96 multiplied by 0.25. Now it is just a matter of taking square roots on both sides. If we do that, we're going to get 0.99 meters per second to the east as our initial velocity of the bullet block system. Let's move to 4.3.2. 4.3.2, initial velocity of the bullet before striking the block. Before striking, there is no frictional force because we are told that we can neglect the effects of air resistance. So we can say that the sum of the momentum before will be equals to the sum of the momentum after. For the bullet, we have a mass of 0.005 and an initial velocity we are interested in. For the block, we have a mass of 3 kgs and an initial velocity of 0 because it was at rest. As the bullet gets embedded on the block, we have a mass of 3 plus 0.005 and a velocity of 0.99, which we just calculated in 4.3.1. So this is 0.99. So 0.005 VI is equals to 3.005 multiplied by 0.99. We're dividing both sides by 0.005. So Vi, let's divide here by 0.005, will be equals to 594.96 meters per second to the east. Something cool to think about. This is 594 meters per second. It is greater than the speed of sound, meaning that if you were to get shot by this bullet, you would hear the sound after getting shot. This is laziness, if I can say, more especially because this same problem was in the June examination. But anyway, let's see what is happening. So we have a pulley system with a mesh piece operated by an electric motor. It is used to lift a load of 120 kgs. Look at this. The load is said to be 120 kgs, and on the diagram, it is 125 kgs. Do you see what I'm talking about? Okay, cool. Vertically upwards at a constant speed, as shown in the diagram below. So they're moving at a constant speed. The load covers a distance of 6.8 meters in 0.01 seconds. Neglect all effects of friction. The first question, 5.1, define in words the term power as applied in physics. That is the rate at which work is done. Power is the rate at which work is done. Let's move to 5.2. Calculate the work done by the gravitational force on the load. So what am I supposed to use now? Am I supposed to use 125? Am I supposed to use 120? It's just a mess. Okay, fine. The work done by gravitational force is equals to the force by gravity multiplied by delta y cos of theta. So let's go ahead and substitute. Fg is equals to the mass. Let's take 125 multiplied by the gravity, which is 9,8. Delta y, it covers a distance of 6.8 meters. So we have 6.8 multiplied by cos of theta. Well, gravity is acting downwards, obviously, but the load is moving upwards. So we have an angle of 180 degrees. If you put that on your calculator, you're going to get minus 8,330 joules as the work done by the gravitational force on the load. And now 5.3, determine the average power output required by the electric motor to lift the load through 6.8 meters in 0.01 seconds. So the key takeaway here is the fact that they are moving at a constant velocity. So we can set up our equation in the following ways. Work net is equals to change in EK. If it is constant velocity, then change in EK is obviously going to be equals to 0. But let's look at the forces that are acting on the system. We have the work done by gravitational force on the load, and we have the work done by the motor. The mesh piece is doing positive work. It is going down, and there's gravitational force on it that is also going down. So the work there is positive. We can set up our equation in the following way. The work done by the motor plus the work done by the mesh piece plus the work done by Fg on the load is equals to 0. We want the work done by the motor. We have the work done by Fg on the load. We just need to find the work done by the mesh piece. Let's find the work done by the mesh piece separately. The work done by the mesh piece will be equals to F, which is gravitational, 100 multiplied by 9.8. The distance covered, 6.8, and the cos of 0. We have already determined that the mesh piece is doing positive work. We're going to get 6,664 joules. Now, if we substitute back in our equation, the work done by the motor plus 6,664 minus 8,330 is equals to 0. So the work done by the motor is equals to 8,330 minus 6,664. You're going to get 1,666 joules. This is the work done by the motor. But we're looking for the power. The power is the rate at which work is done. So we're just going to have 1666 divided by the time, 0.01. We're going to have 166,600 watts. 6.1.1 state the Doppler effect in words. Well, I'm just going to leave that one to you and go straight to 6.1.2. A physics learner clock radio awakens her with a steady and irritating sound of frequency 600 Hz. One morning it malfunctions and cannot be turned off. In frustration, the learner drops the clock radio out of a 4th-story dorm window 15 meters from the ground. Assume that the speed of the sound is 343 meters per second. Ignore the effects of air resistance. Calculate the frequency that the learner hears just before the clock radio strikes the ground. So the frequency observed by the learner will be equals to V plus or minus VL divided by V plus or minus Vs multiplied by the frequency of the source. Frequency of source, we have 600, so there is no problem there whatsoever. And then V, the speed of sound in air, it is given to us 343 meters per second. The velocity of the listener is stationary. The listener is in her room. So we have that it is equals to 0. I think what we need is the velocity of the source. We want the velocity of the clock before or just as it strikes the ground. Let's gather our information and see which equation we need to use. We have the displacement, which is 15 meters. We have our acceleration, obviously, 9.8. We have VI, which is equals to 0, because the learner dropped the clock. And what else do we have? I think that is all we need. We are looking for VF. So the simplest formula here to use should be VF squared is equals to VI squared plus 2A delta Y. So VF squared will be equals to VI, that is 0. So we have 0 squared plus 2 multiplied by the acceleration. Let's take up as positive. So our acceleration will be minus 9.8 and delta Y will be minus 15. And if we take square roots on both sides, we're going to get VF being equals to 17.15 meters per second. And just like that, we have the velocity of the sound source. So we can go ahead and substitute now. FL is equals to 343 plus or minus 0 divided by 343 plus the velocity of the source. The source is moving away, so we're supposed to have a plus sign on the denominator. So plus 17.15. Everything multiplied by the velocity of the source, which is 600 Hz. If you put that in your calculator, you should get 571.43 Hz. You need to be comfortable with doing this on Doppler effect, because it is a very common trend that I'm seeing. We have to calculate VS or VL these days, some way, somehow, before we substitute into FL. It is a new trend that I'm starting to see. So let's be vigilant. Let's go ahead and find more problems that involve these kind of situations and familiarize ourselves with such. 6.1.3. Explain the change in frequency observed by the listener with reference to the speed of the radio clock. So as the clock is going down, obviously, under the influence of gravity, then the velocity of the source is increasing. We know fully well that the frequency observed by the listener is equals to V divided by V plus Vs multiplied by the frequency of the source. So if Vs is increasing, then FL should be decreasing. The frequency observed by the listener should be less than that emitted by the sound source. 6.2. A helium line from the spectrum of the sun has a frequency of 6.2 times 10 to the power 14 Hz. The frequencies of the same helium line from the Earth, which observed in the line emission spectrum of two stars, are: for star X, we have 6.24 times 10 to the 14 Hz, and for star Y, we have 6.04 times 10 to the power 14 Hz. Yeah, this is an interesting one because instead of having the wavelength, we are given the frequencies of distant stars. Usually it is wavelength, so it is quite, an interesting question. 6.2.1, which one of the stars, X or Y, has a redshift? So the one with a smaller frequency has a redshift because it has a higher wavelength. So that is star Y. And 6.2.2, in which direction, away from the Earth or towards the Earth, does star X move? Star X has a higher frequency than our reference point, 6.2 times 10 to the power 14 Hz. So it should be moving towards the Earth. We're supposed to state Coulomb's law in words. Well, the electrostatic force that a point charge exerts on another is directly proportional to the product of the magnitude of the charges and inversely proportional to the squared distance between them, not between their centers. I do see a lot of people making that mistake, saying between their centers. It is the squared distance between them and not their centers. Right, that is 7.1.1. Let's look at 7.1.2. Draw a labeled free body diagram for the sphere X when at rest. Like I always say, when you're supposed to draw a free body diagram, before you start thinking about anything else, put the weight first, because it is always there in our scenarios. So we have the weight and then we have the tension. As you can see on our diagram, we should have something like that. And then sphere X is positive and sphere Y is negative. There's a force of attraction in between the two. So we'll have a force pointing to the right. That is our free body diagram. We have 3 marks and we have 3 forces like we would expect. Let's go to 7.1.3. Let's calculate the electrostatic force exerted by sphere X on charge Y. Well, F is equals to K, Q1, Q2 divided by R squared. We know fully well that K is equals to 9 times 10 to the power 9. As our definition says, the magnitude of the electrostatic force is directly proportional to the product of the magnitude of the charges. Keyword, magnitude. So we're supposed to only substitute the magnitude and not include the direction or the sign, so to say. We're going to have 6 times 10 to the minus 7 as the charge of sphere X, and 9 times 10 to the minus 7 as the magnitude of charge Y. Everything divided by the distance between them, which is 0.15 squared. Right, so that is the electrostatic force that the two charges are exerting on each other. If you put that in your calculator, you shall get 0.22 newtons. Let's go ahead and do 7.1.4. Let's calculate the angle theta shown in the diagram. So our angle theta is between the y-axis and the tension. Usually our angle is here. When our angle is there between the x-axis and the tension, to find the x component, we would use cos, and to find the y component, we would use sine. But if it is up there, then it is the other way around. For x, we're going to use sine, and for y, we're going to use cos. Right, that is something to think about. So let's go back to our free body diagram. Our sphere is stationary. That tells us that the weight and the y component of the tension are balanced, and the electrostatic force and the x component of the tension are balanced. That's what we know. That's what we can try and use to get to our answer. So what are we saying? we're saying that Ty is equals to the weight because our sphere is stationary. What is Ty? Ty is the tension multiplied by cos of theta. If our angle was here, we would be using sine, but it is up there, so we use cos. And this is equals to the weight. The weight is the mass multiplied by the gravitational acceleration. So the tension multiplied by cos of theta will be equals to the mass. I think our mass is 8 times 10 to the minus 2. And the G is just 9.8. If we make the tension the subject of the formula, we're going to get tension being equals to 8 times 10 to the minus 2 multiplied by 9.8. Everything divided by cos of theta. As you can see, we have two variables here. We have our tension and theta. We need to set up another equation so that we can solve simultaneously. Let's go ahead and do that. We said that the forces along the y are balanced. The same is true with regards to the forces along the x. We have Tx being equals to the electrostatic force. What is Tx? In our case, Tx is going to be T sine of theta being equals to the electrostatic force. But we know what the electrostatic force is. That is 0.22. So we're going to have the tension being equals to 0.22 divided by sine of theta. This is equation 2. Well, if these two things are all equals to the tension, then those two things are equals to each other. What are we saying? We're saying that 8 multiplied by 10 to the minus 2 multiplied by 9.8 divided by cos of theta is equals to 0.22 divided by sine of theta. I have cos of theta and sine of theta. If I divide sine of theta by cos of theta, I'm going to get tan of theta. And my problem is simplified. Let me try and achieve that. If I cross multiply, I'm going to get 8 times 10 to the minus 2 multiplied by 9.8 multiplied by sine of theta being equals to 0.22 multiplied by cos of theta. Okay, I'm going to divide both sides by cos of theta because sine of theta divided by cos of theta is tan of theta. So let me divide both sides by cos of theta. After dividing both sides by cos of theta, I'm dividing both sides by 8 times 10 to the minus 2 multiplied by 9.8. If I do that, I'm going to have something that looks like the following. Sine of theta divided by cos of theta is equals to 0.22 divided by 8 times 10 to the minus 2 multiplied by 9.8. Sine of theta divided by cos of theta will become tan of theta. And this is equals to 0.22 divided by 8 times 10 to the minus 2 multiplied by 9.8. Now I just need to say theta is equals to tan arc of 0.22 divided by 8 times 10 to the minus 2 multiplied by 9.8. And if you put that in your calculator, you should get theta being equals to 15.4 degrees. That is 7.1.4. Let's go ahead and do 7.1.5. We're supposed to find the tension in the wire. We have our angle theta, which is equals to 15.4 degrees. And we have a few equations for the tension. The tension is equals to, let's go ahead and pick one equation. We have tension being equals to 0.22 divided by sine of theta. That is the easier one. So let's go ahead and use that one. 0.22 divided by sine of theta. So the tension is equals to 0.22 divided by sine of 15.4. And our tension is equals to 0.83 newtons. Let's go ahead and do 7.2. Looks scary, but it is not. 2-point charges Q1 and Q2 with charges minus 16 times 10 to the minus 7 and plus 4 times 10 to the minus 7 columns respectively are placed 3 meters apart as shown in the diagram. Below, as we can clearly see, the net electric field at point P due to the presence of 2 point charges is 0. Determine the value of X shown in the diagram. So we're given the net electric field, so we know what we are going to use. The first thing you should be saying is that E, the electric field, is equals to KQ divided by R squared. At least now we have a mark. Everything can go wrong, but at least now we have a mark. Let's have a free body diagram. Yeah, what are we without a free body diagram? We will assume that at point P, there's a positive charge. So Q2 is positive. So it means that Q2 is pushing a charge at point P away. So let's call this E2, as it is an electric field due to charge Q2. And at Q1, we have a negative charge. If we are assuming that P is positive, then we're going to have E1 in that direction. So E net will be equals to E2 minus E1. We know that E net is 0. So basically, E1 is equals to E2. Now we can go ahead and write our formulas. KQ divided by R squared is equals to KQ divided by R squared. What is K? 9 times 10 to the power 9. And then the charge of Q1, 16 times 10 to the minus 7 divided by R squared. So how far is Q1 from P? It is 3 plus X meters from P. Don't make a mistake and say that it is 3 meters away. So here we're going to have 3 plus X squared being equals to 9 times 10 to the power 9 multiplied by the charge of Q2. That is 4 times 10 to the minus 7 divided by the distance between Q2 and P. It is X meters. So we're going to have X squared. In a situation like this, things are going to start cancelling out. For instance, 9 times 10 to the power 9 is going to cancel out with 9 times 10 to the power 9. Another values that are going to cancel out, times 10 to the minus 7 is going to cancel out with times 10 to the minus 7. So now we are left with 16 divided by 3 plus X squared being equals to 4 divided by X squared. If you want to complicate your life, go ahead and cross multiply. And after doing that, solve this bracket. That's what you do when you want to complicate your life. The easy way out is taking the square roots on both sides. Let me show you what's going to happen. If we take square roots on both sides, instead of having 16, we're going to have 4. And instead of having 3 plus X squared, we're just going to have 3 plus X being equals to square root of 4 to square root of X squared, X. Simplified. Now we can cross multiply. We're going to have 4X being equals to 6 plus 2X. 2X to the left hand side, we get 2X is equals to 6. X is equals to 3 meters. And we are done. The maximum energy provided by a battery per unit charge passing through it. That is 8.1. Let's go ahead and look at 8.2. State the purpose of placing the switch next to the 8 ohm resistor. Let's go through our equation statement and see what is happening. So grade 12 physics learners are conducting an experiment to determine the EMF and internal resistance of a battery. They have access to an ammeter but do not have access to a voltmeter. They set up the circuit shown in the diagram below. That is the information we have. Let's go back to our equation again. State the purpose of placing the switch next to the 8 ohm resistor. They are placing the switch next to the 8 ohm resistor so that they can control the current in the circuit by changing the resistance. The only thing they have access to is an ammeter. Placing a switch right there allows them to control the current by changing the resistance. That is 8.2. Let's look at 8.3. The results of the experiment are shown in the table below. When the switch is open, we have a current of 4 ampere. And then when the switch is closed, our current is 6 amps. 8.3.1, we're supposed to determine the internal resistance of the battery using EMF is equals to the current multiplied by the external resistance plus the internal resistance. Let's look at our case when the switch is open and see what we're gonna get. When the switch is open, there is not going to be current flowing in this path. So we just have the 8 ohm resistor and the 0.4 ohm bulb in series. So our total external resistance will be 8.4 when the switch is open. Our EMF is going to be equal to the current multiplied by the external resistance, which is 8.4 plus the internal resistance. We have two variables, the EMF and the internal resistance. We need to call this equation 1 and set up another equation. Now, when the switch is closed, when the switch is closed, the EMF is still the same. It doesn't change unless you change the power source. The current is 6 ohm, but we need the external resistance. Let's go ahead and look at our diagram. When the switch is closed, the 8 ohm resistor is in parallel with the other 8 ohm resistor. So we're supposed to calculate resistance in parallel. We're going to have Rp being equals to R1 multiplied by R2 divided by R1 plus R2. R1 and R2, they are both 8 and 8 divided by 8 plus 8. 8 multiplied by 8, that is 64. 8 plus 8, that is 16. 64 divided by 16, that is 4. So our Rp is equals to 4. So here the effective resistance is 4 ohm. But we have this 0.4 ohm. So our total external resistance is 4 plus 0.4, which is 4.4. Let's get rid of all this and substitute 4.4 in our equation. So we have 4.4 plus our internal resistance. This is our equation 2. We're saying that the EMF stays the same. So we can equate these two equations. We're going to have 4 multiplied by 8.4 plus the internal resistance being equals to 6 multiplied by 4.4 plus the internal resistance. Now it is just a matter of solving for R, and we're going to have our internal resistance. Let's go ahead and do that and see what we're going to have. On the left hand side, we're going to have 33.6 plus 4R being equals to 26.4 plus 6R. 26.4 to the left hand side, we're going to get 7.2 being equals to 2R. If we divide both sides by 2, we're going to get R being equals to 3.6 ohms. So that is our internal resistance. 8.3.2, we are looking for the EMF of the battery. We have the internal resistance, so that should be quite easy. We can substitute R in equation 1 or equation 2. Let's substitute it in equation 1. In equation 1, we have 33.6 plus 4 multiplied by R. R is 3.6. So let's go ahead and substitute it. We're going to get 48 volts. If you substitute it in equation 2, you should still get the same thing. Let's carry on. Let's do 8.4, 8.4.1. Calculate the power dissipated in the battery when the switch is closed. The power dissipated in the battery when the switch is closed. Right, let's go to our sketch. When the switch is closed, the current is 6 ampere. The internal resistance is 3.6. So that doesn't change. We know fully well that the power is equals to I squared multiplied by R. Well, the power is equals to V squared divided by R, and it is equals to V multiplied by I. But looking at the variables we have, it is wise that we use I squared multiplied by R, because we don't have to find a variable and substitute again. If we go ahead and do that, we're going to have 6 squared multiplied by 3.6. This is equals to 129.6 watts. That is the answer to 8.4.1. Let's look at 8.4.2. Energy dissipated in the bulb in 6 minutes when the switch is open. When the switch is open, our current is 4 ampere. Our time is 6 minutes. So we have 6 minutes multiplied by 60, 360 seconds. What else do we have? The bulb. We have the resistance of the bulb. it is equals to 0.4 ampere. We want to find the energy dissipated. So the work is equals to I squared multiplied by R multiplied by delta T. We are picking this equation because of the variables we have. The current, that is 4 squared multiplied by the resistance 0.4 multiplied by the time 360. This will be equals to 2304 joules. 8.4.2. The last question, 8.5. How is the brightness of the bulb affected when the switch is opened? Stayed only brighter, dimmer, or not change? When the switch is open, we have a current of 6 ampere. And when it is closed, we have a current of 4 ampere. So we can clearly see that the current that the bulb is experiencing is going to be reduced when the switch is opened. So it should glow dimmer. Write down the energy conversion which takes place in a generator. We know that generators, they turn mechanical energy to electrical energy, while motors, on the other hand, they turn electrical energy to mechanical energy. That is 9.1. Let's go ahead and look at 9.2. Write down the type of generator represented by diagram X. If you look at diagram X, you're going to realize that we have split rings. And as soon as we see split rings, we know that we have a DC generator. 9.2.2, we have slip rings, and that is a component which we find on an AC generator or an AC motor, the presence of slip rings. And in DC generator, it is split rings. There's a difference between the two. Let's go ahead and look at 9.3. We're supposed to state the difference between the two generators by referring to the components shown in the diagram of which they consist. I mean, this is question 9.2 really, because how are you able to tell that diagram X is a DC generator? And how are you able to tell that diagram Y is an AC generator? You are able to tell because in a DC generator, in diagram X, we have split rings. And in diagram Y, the AC generator, we have slip rings. So if you get the answers to 9.2, then you should get 9.3 wrong. Because how did you arrive to your answer for 9.2 if you get in 9.3 wrong? Doesn't make any sense. Let's look at the question that follows. 9.4, 9.4.1. The generation diagram Y produces a potential difference with a root mean square value of 220 volts. 9.4.1, define in words the term RMS voltage. The AC potential difference which dissipates the same amount of energy as an equivalent DC potential difference. That is RMS voltage. 9.4.2, calculate the peak maximum potential difference of the generator. So we're looking for Vmax, but we know that Vrms is equals to Vmax divided by square root of 2. We have Vrms, it is 220 volts. So we're going to have Vmax being equals to 220 multiplied by square root of 2. What is 220 multiplied by square root of 2? That is 311.13 volts. The last question, 9.4.3. Sketch a graph of potential versus time to indicate one full rotation of the coil. Clearly indicate the values of the following on the diagram: the RMS value and the peak potential difference. We're interested in diagram Y. Diagram Y is the AC generator. So we're supposed to have a graph of potential difference versus time for an AC generator. It looks different from the potential difference versus time graph of a DC generator. In an AC generator, the current alternates. So we're going to have something like this. We're supposed to indicate Vmax and Vrms. Vmax will be somewhere here with a value of 311.13. And then we're going to have VRMS somewhere here with 220 volts. On the x-axis, we have time in seconds, and on the y-axis, we have the potential difference in volts. The minimum amount of energy required for electrons to be emitted from a metal surface. That is the work function, 10.1. Let's look at 10.2. Prove by means of an appropriate calculation that the work function of the cathode is 3.68 times 10 to the minus 19 joules. What's happening here? Let's look at our equation statement. In a photoelectric effect experiment, the maximum kinetic energy of the photoelectrons ejected from a certain metal surface is 4.48 times 10 to the minus 19 joules. When the wavelength of the incident light is increased by 50%, the maximum kinetic energy decreases to 1.76 times 10 to the minus 19 joules. So let's go ahead and look at our situation. When light of an unknown wavelength is shown on the metal, the maximum kinetic energy is 4.48 times 10 to the minus 19 joules. Let's go ahead and set up that equation and see what we're going to have. We know that Planck's constant multiplied by the speed of light divided by the wavelength is equals to the work function plus the maximum kinetic energy. Planck's constant is a constant. We can leave it as it is. C, speed of light, we can leave it as it is. And the wavelength, which is unknown at this point, we're going to leave that as it is. The work function is what we're looking for. Obviously, we're going to leave it as it is. So the only thing we're substituting for here is EK max. Let's go ahead and see how that will look like. So we're going to have HC divided by wavelength being equals to the work function plus EK max. EK max is 4.48 times 10 to the minus 19 joules. This is equation 1. When the wavelength is increased by 50%, the maximum kinetic energy decreases to 1.76 times 10 to the minus 19 joules. So how is our equation going to look like? We still have H, we still have C, but instead of having wavelength, it is increased by 50%. So we're going to have 1.5 wavelength. That is what you get when you increase a quantity by 50%. This is equals to the work function plus EK max, which is 1.76 times 10 to the minus 19 joules. This is equation 2. So we need to play around with these two equations and ultimately get the value of the work function. Well, let's get rid of this 1.5 so that we can have HC divided by wavelength and equate the two equations. How can we possibly do that? We can multiply by 1.5 on the left hand side and on the right hand side. If we do that, we're going to have H multiplied by C divided by wavelength being equals to 1.5 work function plus 1.76 times 10 to the minus 19 multiplied by 1.5. So we can equate HC divided by wavelength. If we do that, we're going to get 1.5 work function plus 1.76 times 10 to the minus 19 multiplied by 1.5 being equals to the work function plus 4.48 times 10 to the minus 19. Let's take the work function to the left hand side and 1.76 times 10 to the minus 19 multiplied by 1.5 to the right hand side. 1.5 work function minus work function, that is going to be 0.5 work function. This is equals to 4.48 times 10 to the minus 19 minus 1.76 times 10 to the minus 19 multiplied by 1.5. We divide both sides by 0.5. Our work function is going to be equals to 3.68 times 10 to the minus 19. We are dividing both sides by 0.5. That is 10.2. Let's go ahead and look at 10.3. Hence, find the initial wavelength of the incident light. We have the work function and a couple of equations. Let's use equation 1. It looks easy on the eye. So H multiplied by C divided by wavelength is equals to the work function plus EK max. The work function is 3.68 times 10 to the minus 19 plus 4.48 times 10 to the minus 19. So the wavelength is going to be equals to Planck's constant, that is 6.67 times 10 to the minus 34 multiplied by the speed of light, 3 times 10 to the power 8 divided by 3.68 times 10 to the minus 19 plus 4.48 times 10 to the minus 19. The wavelength is equals to 2.45 times 10 to the minus 7 meters. That is 10.3. Let's answer some conceptual questions. 10.4 and 10.4.1. How does each of the following affect the maximum kinetic energy of the photoelectrons? State only increases, decreases, or remain the same. We're interested in EK max, right? And then 10.4.1, using incident light of a shorter wavelength. If we're using incident light of a shorter wavelength, that increases the frequency. If the frequency increases, EK max increases. So the answer to 10.4.1 is increases. Let's look at 10.4.2. Using a cathode with a higher work function. Well, EK max, if you rearrange one of the equations we have, you will get E minus the work function. So using a photocathode with a higher work function will decrease EK max. So the answer to 10.4.2 is decreases. 10.4.3, using incident light of a greater intensity. The intensity just increases the number of photons being sent to the cathode. It doesn't affect the frequency whatsoever. So the answer to 10.4.3 is remains the same.